In this video, I'll be going through the 2022 May-June IGCSE Physics Theory Core Paper version 1. Figure 1.1 shows a dripping tap and a measuring cylinder. The water drops all have the same volume. The drops fall from the tap at equal time intervals. The student collects 200 of the drops in a measuring cylinder. The total volume collected is 60 cm3. Calculate the average volume of one drop of water. To find our volume, we need to take our total volume of 60 and divide it into our 200 drops, which gives me 0.3 cm3. Another student uses a stopwatch to measure the time taken for the tap to produce 200 drops. Figure 1.2 shows the time reading on the stopwatch. Determine the time in seconds for the tap to produce 200 drops. To find our time, we take our 3 minutes, which is 3 lots of 60, and add on our 46.5 seconds, which gives me 226.5 seconds. Determine the average time interval between one drop starting to fall and the next drop starting to fall. For this, we need to take our total time of 226.5 and divide it between our 200 drops, which gives me 1.1 seconds to two significant figures. Figure 1.3 shows the volume of water collected in the measuring cylinder by another student. Determine the volume of water in the measuring cylinder in Figure 1.3. We see our water line here, and because we have 5 increments between 80 and 90, each increment must be an increase of 2. Because we're 2 increments above 80, our mark must be at 84. Figure 2.1 shows the speed-time graph for two cars A and B. Determine the speed of car A at time equals 10 seconds. Here is our line of 10 seconds, which we can follow up to here, which given that this mark here is 9.0, and this is 9.2, and this is 9.4, our mark looks to be halfway between, which is going to be 9.3. State and explain which car, A or B, has the greater acceleration during the first 10 seconds. Use information from the graph in Figure 2.1 in your explanation. On a speed-time graph, the acceleration is the slope of the line. We see that the slope for A is steeper than the slope for B, so car A must have the greater acceleration. Car A has a greater acceleration because the slope is steeper. Describe the motion of car B after 30 seconds. Here is our 30 seconds, at which we see that car B is maintaining a constant speed of 16 meters per second. Constant speed of 16 meters per second. Calculate the distance moved by car B from time equals 0 to time equals 30 seconds. The distance travelled on a speed-time graph is the area underneath the graph, which is this area here. As you might note, this represents a triangle with a base of 30 and a height of 16. The area of a triangle is given by the equation half base times height, where our base is 30 and our height is 16, which gives me 240 meters. Figure 3.1 shows a metal block and its dimensions. Calculate the area of the metal block in contact with the ground. Our area is a rectangle, which means the equation is just base times height, which is 12 times 2, giving us 24 centimeters square. The mass of the metal block is 0.84 kilograms. Calculate the weight of the metal block. We can calculate the weight force as just the mass times the gravitational acceleration, where our mass is 0.84 and our gravitational acceleration is just 10, given on the front page, which gives us 8.4 newtons. A different metal block has a weight of 24 newtons. The area of this metal block in contact with the ground is 4 centimeters square. Calculate the pressure of this block on the ground. The equation for pressure is just force divided by area, where our force is 24 and our area is 4, which gives us 6 newtons per centimeter square. Figure 4.1 shows an electric motor and pulley wheel being used to raise a load M. The electric motor uses a belt to turn the pulley wheel. When the electric motor lifts the load, it transfers energy. Figure 4.2 shows the energy transfers. Write on Figure 4.2 to complete the label in each box. The first label is done for you. Our electrical energy is used to make our load move. Because it's moving, that is kinetic energy. As the load is lifted against gravity, we are also storing gravitational potential energy. As a byproduct of this process, due to various kinds of friction, we're going to get wasted energy in the form of thermal energy. Figure 4.3 shows the force on the pulley from the load M. The weight of load M is 2.5 newtons, and the weight acts at a distance of 20 centimeters from the pivot of the pulley wheel. Calculate the moment of the weight of load M about the pivot. Our moment is just the force times the distance, where our force is 2.5 and our distance is 20 centimeters, which gives us 50 newton centimeters. Describe how a wind turbine generates electricity from energy in the wind. The wind has kinetic energy, which is used to turn the blades. The blades rotate a turbine, powering the generator, producing electricity. Apart from cost, state 2 advantages of generating electricity using wind turbines compared with using a power station that burns coal. First of all, wind is renewable, and burning coal produces greenhouse gases. Apart from cost, state 2 disadvantages of generating electricity using wind turbines compared with using a power station that burns coal. It only functions if wind is present and requires more area. A teacher fills a copper can with solid wax and heats the can. She measures the temperature of the wax every minute. She continues heating once the wax has melted and stops heating when the wax is boiling. State the term used for the process that transfers thermal energy through the copper. This is conduction. Figure 6.1 shows how the temperature of the wax changes as it is heated. Using the graph in Figure 6.1, determine the melting point of the wax, which is this plateau here, which is 80 degrees. Because the temperature stops changing, where the energy is no longer being used to increase the temperature of the wax, it's being used to change its state. For the same reason, the boiling point of the wax must be here, which represents 170 degrees. The time at which the wax starts to boil must therefore be the start of this plateau, which is 26 minutes. Describe the molecular structure of the wax in terms of the arrangement, separation, and motion of its molecules when it is a solid and when it is a gas. For solid wax, the arrangement is fixed, whereas for a gas, the molecules are free to move. For a solid, there is low separation. For a gas, there is high separation. As for the motion, the molecules in solid wax vibrate in place, whereas for a gas, they move randomly at high speeds. Figure 7.1 shows the displacement of particles in a water wave. Using the information in 7.1, determine the wavelength of the wave. The wavelength of the wave is 1 cycle, which is 8 centimeters. The amplitude is this dimension here, which is 1.5. The water waves travel from deep water into shallow water. The water waves have a lower speed in the shallow water. Figure 7.2 shows wavefronts for the waves in deep water to the left of the boundary. On Figure 7.2, complete 3 wavefronts for the waves in shallow water to the right of the boundary. If we imagine our wavefront continuing across the boundary, our wave travels faster in deep water and slower in shallow water. This means that our wavefronts are going to rotate around clockwise and look something like this. State the term for the process at the boundary in Figure 7.2. This is refraction. State the name of one type of electromagnetic wave with a wavelength shorter than that of visible light, in order of increasing frequency and therefore decreasing wavelength. We have radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Our visible light is here. The types with a smaller wavelength are therefore ultraviolet, X-ray, and gamma ray. Any will do. State one use of the type of wave you have given in CI. Ultraviolet can be used to sterilize medical equipment. If you had written X-ray or gamma rays, you could say medical imaging. Figure 8.1 shows a bar magnet on a piece of card. Describe an experiment to determine the pattern of the magnetic field lines around the bar magnet. You may draw on figure 8.1 if it helps to explain your answer. We could place multiple compasses at different positions around the magnet. The arrows will point in the pattern of the field lines. A student has a bar magnet and a metal bar with ends labelled X and Y. The student moves the metal bar close to either pole of the bar magnet. Figure 8.2 and 8.3 show the forces on the metal bar in each case. State and explain what these results reveal about the metal bar XY. Because the bar is attracted to both poles, the metal bar must be unmagnetized. Figure 9.1 shows an electric circuit, which includes uninsulated resistance wire XY. A teacher shows some students how to complete the circuit by placing the contact C at various positions on the wire XY. The students place contact C at Y, they measure the current on the ammeter, then they move the contact C along the wire from Y to X. State and explain the effect on the ammeter reading when they move the contact C from Y to X. As the path along the wire decreases, the resistance will decrease, causing the current to increase. Calculate the reading on the ammeter when contact C is at X. If our contact C is at X, we will have no path along this wire, and so no resistance. That means the entire resistance of the circuit is going to be 8 ohms with a voltage of 6. We know that V is equal to IR, which means that our current and therefore our ammeter reading is going to be V over R, where our voltage is 6 and our resistance is 8, which gives me 0.75 amps. The students move contact C to point P. The resistance of the wire between X and P is 20 ohms. Calculate the total resistance of the resistance wire between XP and the fixed resistor. These resistances are in series, and so our total resistance is going to be the sum of our resistances, which is 20 plus 8, giving us 28. The electric current in the circuit produces two effects. Place a tick in the boxes next to these two effects. Not gravitational. Electric current does generate a magnetic field. There will also be heating because we have electrical resistance. There's no reason to expect that there will be sound or X-ray emissions. A microwave oven has a metal case and is connected to a 240 volt electricity supply. The microwave oven is fitted with a 13 amp fuse, and an earth wire is connected to the metal case of the microwave oven. A fault occurs, and the live wire of the microwave oven touches the metal case. Explain how the fuse and an earthed metal case protect the appliance and the user. A large current will flow through the live and earth wire, melting the fuse and stopping the current. This will protect the user from electrocution and the appliance from overheating. The electric circuit for the microwave oven includes a transformer. The voltage to the primary coil of the transformer is 240 volts. The number of turns on the primary coil is 70. The number of turns on the secondary coil is 560. Calculate the secondary voltage for the transformer. The ratio of our voltages is equal to the ratio of our turns. Solving for Vs by multiplying both sides by Vp. Putting in our numbers gives me 1920. A teacher demonstrates the types of emission from a radioactive source. He uses different materials to absorb the emissions. Figure 11.1 shows the equipment. The teacher places a material between the radioactive source and the detector. The counter shows the count rate for the emission that reaches the detector. The teacher records the count rate. He repeats the experiment for different materials. State whether the source emits alpha particles. Use the information from table 11.1 to give a reason for your answer. Alpha particles would be blocked by paper. Because the count rates are roughly the same, there must be no alpha particles. Paper blocks alpha. Because the count rate is not significantly lower, there must be no alpha. State whether the source emits gamma rays. Use information from table 11.1 to give a reason for your answer. A block of lead would block a portion of the gamma rays. Because we see that the count rate is significantly lower, there must be gamma rays. The lead would block a significant portion of the gamma rays. Since the count rate is significantly lower, there must be gamma rays. And we're done.